Roland Minton. These are some of my favorite math stories. In this episode, Mathematics is Decisive. We will analyze a story about a tragically indecisive person. As we will see, the story itself is indecisive, although ambiguous would be a better word. To come to any sort of conclusion about the story, we will have to apply some mathematical thinking. The power, and in some cases the limitations, of math are in its use of definitions and axioms to precisely state a problem. From there, logical deduction takes us to a conclusion. Human languages are wonderfully flexible. Poets and lyricists take advantage of this to imply emotions and leave space for the audience to create their own associations and meanings. Different people can come up with entirely different meanings of songs or poems and all be correct in their interpretations. For better or worse, mathematics uses language in a different way, where some interpretations are demonstrably incorrect. The following story appeared in the national newspaper column. A young student is supposed to be studying at home, but is tempted to slip out to the local theater to see a movie. After heading from home to the theater, the person feels guilty and turns around 3/4 of the way there. But after walking 3/4 of the way back home, the person really wants that movie, turns around, and goes back to the theater. But after getting 3/4 of the way back there, the person turns around again. If this is repeated indefinitely, where does the person end up? When I first saw the puzzle, it was not obvious to me that there's a crucial ambiguity in the description. Can you see it? I had to start trying to solve the puzzle to see the difficulty. To get started, define a variable x for the person's position. X equals 0 represents home, x equals 1 the theater. Let's track the person's movement. Starting at x equals 0, 3/4 of the way to x equals 1 would put us at x equals 3/4. So far, so good. We next go 3/4 of the way back to x equals 0. This may be a little bit harder, but the distance from x equals 3/4 to x equals 0 is 3/4. And 3/4 of that is 3/4 times 3/4, or 9/16. Starting at x equals 3/4, going in the negative direction 9/16 puts us at x equals 3/4 minus 9/16, and this computes to be x equals 3/16. It'll turn out that we don't really want this version of x, but we'll get to that in a bit. Now, go 3/4 of the way back, and we've got a problem. Is this 3/4 of the way to the theater at x equals 1, or 3/4 of the way to the last turnaround point at x equals 3/4? My first thought was to use x equals 1, but the solution given in the column is only correct if you use x equals 3/4. This is the easier problem mathematically. In many cases, decisions made about which option to use are based on mathematical convenience rather than logic. So let's first find the solution using x equals 3/4, and we'll see the more complicated math if we use x equals 1 later. So we're at x equals 3/4 minus 9/16, and we'll see why we really don't want to simplify this to 3/16. We want to go 3/4 of the way to x equals 3/4. The distance from 3/4 minus 9/16 to 3/4 is 3/4 minus 3/16, and we get 9/16 for that distance. Thought of in a different way, our indecisive student walked a distance 9/16 backwards, so this is the distance that we want. 3/4 of this is 3/4 times 9/16, or 27/64. Since we are moving in the positive direction, we want to get to 3/16 plus 27/64 before turning around again. This is looking pretty messy and difficult to find a pattern. A rewrite will help. Let's think of that distance walked as 3/4 squared instead of 9/16. Then 3/4 of that distance is 3/4 cubed. We'll wind up at x equals 3/4 minus 3/4 squared plus 3/4 cubed. Much nicer. Now you can see why it is useful to not compute x as a fraction. Is it clear what happens next? The last distance covered was 3/4 cubed, and 3/4 of that would be 3/4 to the 4th. So this is what gets subtracted when the student heads back home. Continuing indefinitely, we have what's called a geometric series, 3/4 minus 3/4 squared plus 3/4 cubed minus 3/4 to the 4th plus 3/4 to the 5th, and so on. Fortunately, there's a simple formula for what happens when you add more and more terms of this type. Geometric series are distinguished by each term being the previous term multiplied by a particular constant, in this case negative 3/4. If the series starts with c and the multiplicative constant is r, with r between -1 and +1, the sum will converge to c divided by 1 minus r. When c equals 3/4 and r equals negative 3/4, this equals 3/7. So our indecisive students take smaller and smaller steps and get stuck at x equals 3/7, a little less than halfway from home to the theater. Well, this was nice and simple in that a pattern quickly emerged and there was a formula to help us finish the problem. The alternative is shown below. Our student goes from 0 to 3/4 to 3/4 minus 9/16, which is 3/16, and we might or might not want this simplified. In the next leg, the student goes 3/4 of the way back to x equals 1. The distance from 3/4 minus 9/16 to x equals 1 is 1 minus 3/4 minus 9/16, which is 1 minus 3/4 plus 9/16, or 13/16. 3/4 of this distance is 3/4 times 13/16, 39 over 64. And again, I'm not liking the looks of this. So let's go back and not simplify. We'll do 3/4 of 1 minus 3/4 plus 9/16. Multiplying the 3/4 through, that's 3/4 minus 3/4 squared. And thinking of 9/16 as 3/4 squared, another multiplication gives 3/4 cubed. Moving in the positive direction puts us at 3/4 minus 9/16 plus 3/4 minus 3/4 squared plus 3/4 cubed. Okay, well this is really not looking all that good. So let's just try thinking of the problem in a completely different way. An important clue about the solution is that the length x, shown above, equals 51 over 64, which is larger than the previous near-theater turnaround of 3/4. So the student is not shrinking into a single final position, but diverging away to a different solution. Let's track that right-hand turnaround point by doing a full back and forth. Keeping it general, suppose we start at position y to the right. The next step is to go 3/4 of the way back to x equals 0. We'll end up at y minus 3/4 of y, which is just 1/4 y. We'll then go 3/4 of the way towards x equals 1. That distance is 1 minus 1/4 y, and 3/4 of that is 3/4 minus 3/16 times y. Adding that in puts us at 1/4 y plus 3/4 minus 3/16 y, which is 3/4 plus 1/16 y. That's looking pretty good. Now you might wonder how I knew to simplify this instead of looking for a pattern in an infinite series. Well, I didn't. I tried the infinite series and didn't like it. I tried this and it worked. The first right-hand point is at x equals 3/4. So by this formula, the second point would be 3/4 plus 1/16 of that, and then followed by 3/4 plus 1/16 of 3/4 plus 1/16 of 3/4. Multiplying that out, you've got 3/4 plus 3/4 times 1/16 plus 3/4 times 1/16 squared. This is looking good. Got another geometric series. The factor multiplying from one term to the next is 1/16. So the geometric series formula produces starting value of 3/4 divided by 1 minus 1 over 16, which ends up being 4/5. So this is half the solution. The right-hand points converge to y equals 4/5. The left-hand turnarounds are at 1/4 y. We saw that above, and that's 1/5. Our indecisive student walks back and forth between 1/5 and 4/5 of the way to the theater. We ended up using a lot of algebra, but I hope that you could see some problem-solving techniques in there. We started by slowly working out the first couple of steps. In doing so, you do not always want to simplify or compute a numerical value. The best case is for a pattern to emerge that can be exploited to immediately produce the solution. You should simplify or compute or not, depending on whether a pattern starts emerging. The patterns we saw here depended on whether the solution was a single number or a pair of numbers. Sometimes you have to know something about the solution to know how to approach the computations.